First, here is the system architecture for our project that shows how everything is connected. The consumer meter monitors the current and voltage and processes the values to find other parameters, and with the help of a GPS sends time-tagged values to the gateway through a LoRa network. The gateway forwards those received packets to the server through the internet, and from a SCADA software in the server we can access the information sent by the consumer meter. So the primary part of the project are the sensors and measurements. The voltage and current sensors are comparable with the Arduino and convert the high voltages and currents into 0 to 5 volt range of the Arduino's ADC. The Arduino processes these values and scales them to their actual quantities, after which power factor, instantaneous power, and harmonics can be calculated. These values are then going to be sent to the main server through LoRa communication to a Raspberry Pi. The Pi is both Internet and LoRa enabled and can act as a gateway for the end nodes. Measuring the harmonics requires a high sampling rate and enough memory to perform a fast Fourier transform. Since we have to capture up to the fifth harmonic, we sample at around 1000 Hz. We could increase the sampling rate, but due to memory limitations, we can't do that. Here is the full circuit of the AND node. The white cable on the left has a plug on the other end, and the sensors and the output box are wired as shown. The GPS and phase detection circuitry can also be seen to the left of the Arduino. Due to the lockdown, a proper enclosure could not be made. However, the sensors and the other circuitry has been covered with electric tape from below and taped to a cardboard for safety. A relay has also been added to shut off power through a command from the server. Few loads were tested whose waveforms are being shown here. Here is a non-linear switching power supply for a laptop. The current is a chopped sine wave and has a lot of odd harmonics. There is some noticeable phase difference between the voltage and current as well, which is around 90 degrees. Here is the frequency spectrum for the current waveform of the power supply. We can see that the signal contains odd multiples of the power frequency. We can also see that the harmonics for beyond 250 Hz are shown but have drifted towards higher frequency values due to low sampling rate and memory of the Arduino. Here we see the waveform for a fan. The current jumps to a high value due to the high torque when the fan starts and slowly decreases to its steady state value. Here is a magnified view of the previous waveform. We can see that the current is leading the voltage, which is inherent in inductive loads such as the fan motor. The frequency is calculated by inputting the voltage waveform into a zero crossing detector, which gives out a square wave that can be input to a digital pin on the Arduino. Using timers, we can get the on time and the off time, which can then be summed and inverted to get the frequency. LoRa communication is used here to allow for monitoring of power consumption from remote locations. LoRa has the advantage of having very low power usage, so it can be used for years on the same battery. Low power and high range comes at the cost of bandwidth, so this is only good for sending sensor data and short messages. Video streams and pictures cannot be shared readily in this technology. One important thing to note here is that LoRaWAN is not being used here because LoRaWAN depends on locally placed high-power gateways which are not available in Pakistan. Also, we intended to implement a mesh network which is not supported by LoRaWAN, but due to the nature of mesh networks, a third module would be required which couldn't be purchased because of the lockdown. Raspberry Pi is a powerful enough platform to support multiple AND nodes continuously broadcasting data over LoRa. An Arduino is connected through the serial port that handles LoRa communication for the gateway. The Pi itself lacks the software libraries that could interface it with the LoRa module properly. The Arduino has a code running that sends the incoming LoRa traffic to its serial port which can be read by the Raspberry Pi. We made a Python script that reads data from the serial port of the Raspberry Pi, parses it, and then connects the Pi to the server through MQTT protocol. Incoming values of voltage, current, and power from the AND node are then sent to the server as comma-separated values. Ignition is a popular industrial standard SCADA software with many features and ease of use. It also has MQTT support that we have used in the project. MQTT is an Internet protocol that was developed for machine-to-machine communication in the IoT era. It consists of topics that act as variables. They can be subscribed to get their value and can be published to set their value. MQTT brokers act as servers that can redirect messages on topics. Ignition has a module that contains an MQTT broker. In our project, each parameter uses separate topics which map to variables in Ignition. Ignition can then use those variables to update values in its database. Ignition SCADA allows designing of user interfaces and HMIs for user interaction and visualization of parameters. For this project, I designed this user interface which takes data sent from the Pi and displays it. The user interface shows GPS synchronized date and time for each reading, voltage, current, power and power factor and their 3-minute graphs, frequency, and ratio of the magnitude of the harmonics to the fundamental one. Graphs for voltage, current, and power are also available, whose x-axis or the time axis can be changed to show the data over the required date and time. So right now we have a fan and a laptop charger running through our mirror. The odd harmonics are fairly higher than the even ones, which is caused by the switching power supply of the laptop charger. Now if I remove the plug for the fan, these harmonics will have even higher values because the fan was causing a higher magnitude of the 50 Hz waveform, which would make the relative magnitude of the harmonics smaller. I now show the power switch working through the server. The switch off signal is first sent from the server to the gateway, which then forwards it to the end node here. Here I have two voltage readings at two different times on the multimeter, which is the same as shown on the server, which means that the Arduino is measuring the voltage correctly. Here is the Raspberry Pi connected to the Arduino through a serial port and to the router through Ethernet. So here you can see the end node sending the parameters onto the Raspberry Pi gateway. The console shows the Python script running on the Pi that parses the data sent to it and then forwards it to the server. Now here is the user interface with its values getting updates from the gateway. We can see that the power is on and a load is connected. We can also see that the third and fifth harmonics are very high due to the power supply for the laptop that is connected here. And if I turn it off, the laptop stops charging and the current drops to a very small value. The current reading takes some time to settle. Noise in the current sensor causes false readings of small currents. We could rectify them if we had the proper equipment for testing and proper calibrating. Now if I turn it back on, the laptop starts charging again. Trend lines for the parameters can also be seen here, which show data from the last 3 minutes. We can also access the history for these parameters by clicking on the red graph lines. The graphs allow viewing of data from a certain date and time.